I'm Karan. I'm a third-year CS PhD student at Stanford, and I'm going to be talking today about building malleable machine learning systems through measurement, monitoring, and maintenance. A little bit about me. So I obviously come from a research background, so this is going to be a little bit, less from an industry point of view, but hopefully some of the ideas here will translate to things that teams in industry are working on, and we definitely try to work on things that might be interesting to folks in the audience. So let's see how this goes. So let's dive in. I will set some context around kind of the larger work that I'm doing, and do it by kind of defining this ML software hierarchy, which I think is my kind of crude attempt at qualifying the different pieces of work out there and what I think is kind of still needs to get worked on. And the idea is that I think of four blocks here. The first block at the very bottom is the idea of program and run. So this is kind of like standard machine learning. You want to build models and you want to program your data. You want to change your data sets in order to reach a high-performing model for some task of interest. And this is kind of the wheelhouse of pretty much traditional machine learning. This is what we got really good at doing over the past 10 years, really. Then there's this layer on top, which is measuring and monitoring what you are deploying or what the models that you've built. And the idea here is that once you've built a model, you want to understand things like distribution shift, because models typically are not working on static data. Data evolves over time, and so models will degrade as well. You want to understand what these models actually know, and you want to evaluate where they work well, where they fail. So a lot of these desiderata come up when you actually have good models that you have some hope of deploying, because then and only then do you really care about understanding these more fine-grained gaps in performance. Then the next step is improving and repairing models. So once you can measure and monitor, it becomes easier to understand where you can intervene in order to fix gaps in your models, in order to repair them, in order to iterate on your data, which is a pretty popular thing that has kind of started receiving a little bit more attention recently. And really kind of this third piece is a little bit harder because it requires getting the second piece right, which is measuring and monitoring your models. And lastly, we have this kind of, I would say, top level thing, which is interaction. How do humans and machine learning engineers, data scientists, all of the different personas that you might care about, how do they interact with these systems that encompass a lot of these capabilities that are listed here? So in summary, we're kind of doing this pretty well, but there's a ton of stuff to do in this bucket. And so in this talk in particular, I'm going to talk a little bit about measurement, a little bit about monitoring, a little bit about improving models, and kind of give a taste of kind of these different areas and what we've been doing on the research side, and hopefully conclude with some thoughts on interesting directions that I think could spur some more research in this area. So let's dive in. So I'm going to talk about malleability as a concept, and this is something that I just made up basically. So it's kind of a made up thing, but hopefully it captures some of the things that we might care about with machine learning systems. So loosely speaking, I'll define it as the ability to modify a machine learning system over time in order to perform bug fixes, hit performance targets, meet ethical standards, whatever kind of capabilities you might want out of your system. And the crucial thing here is that we might be able to define some system components that help us really kind of nail down what we might be looking for in this malleable ML system kind of framework. So the desiderata, at least from my point of view, that I'm really interested in is you want these stakeholders that I talked about, machine learning engineers or data scientists or data engineers, to be able to interactively measure, so understand fine-grained system capabilities and performance, monitor, track distribution shift or other shifts in your data and its effects over time, and then maintain, which is perform atomic updates to your data and models as data changes or your models degrade or requirements change in your business, whatever it is that that causes some shift. And so Malleability broadly, a malleable system would provide you these capabilities and allow you to do all of these different things easily. And hopefully what that does is makes these machine learning systems a little bit more human-centric and a little bit easier for humans to work with. And hopefully what you'll see in a lot of the other talks as well is like people having kind of attempts at defining abstractions and things to achieve some of these goals. And these are certainly not, exhaustive, but there's some things that I think are important in order to make machine learning work in practice. So one thing I'll say here is that most of the knowledge to do some of these things is tacit currently. So a lot of knowledge about how to actually build systems that have these capabilities are kind of things that people have learned over time as they've been building systems and building up that experience. But it's hidden inside a few large organizations, and then they've kind of built tools to do some of this, but it's not really kind of broadly available to anyone to use. And that's where, startups are coming in the last few years, and they're trying to build some of these tools also in open source and make it easier for people to have access to that. But I think part of the effort is actually taking that knowledge that some organizations, maybe say a Google might have, having done this for longer than other people, and then kind of crystallizing it, and of course, like taking the research advances we've had and putting it together in a nice package for folks to use. So with that, let me dive in. So measurement, just to reemphasize, is understanding fine-grained system capabilities and performance. Monitoring is tracking distribution shift and its effects over time. And then maintenance is performing atomic updates to data and models. So this is the summary of what I'll talk about in this presentation. So let's start with measurement. So you can see I drew these arrows at the top for measurement, monitoring, maintenance, and roughly speaking, I do think there's an ordering, because like you have a bottleneck. You can't fix what you don't measure. So you have to be able to first do measurement, and then you can deploy that into monitoring. And then if you can measure properly, then you can take interventions and corrective action in maintenance. So what we need broadly in machine learning is more fine-grained model metrics across critical slices of data. This is generally a good desiderata to understand what models are doing, and it's kind of the first step, I would say, for fine-grained evaluation. And I'm going to touch on one particular work here that I think Mike talked about in his introduction as well, which is Robustness Gym, which is a fine-grained evaluation toolkit that we've been building on the research side. This is work in collaboration with a few folks at Salesforce Research, Stanford, UNC, and we had a demo earlier this year and have a paper out that you can read, and as well as the code. But that's what I'll talk about. And there's a few other works that I mentioned here, which if you're interested in, you can look at. So let's dive in. So Robustness Gym is our attempt at defining a fine-grained evaluation toolkit. And the idea here is that there are a lot of different ways that you might want to evaluate your models. So coming back to the problem of measurement, there are many different ways you can measure what's actually happening to models inside a system, machine learning system. So there are things like looking at critical data slices, looking at concerns that are driven by, let's say, bias or fairness considerations, looking at sensitivity of your models, invariance to input perturbations, so on. So there's a lot of different ways that people in both research and academia and industry try to evaluate models. And the idea was to bring these together under one kind of umbrella toolkit and hopefully give abstractions that are general and kind of allow you to evaluate your models against a few of these. So on the right, we kind of have the output that you might get from Robustness Gym, which is a report that kind of summarizes evaluations that you can build here. So the summary here is it's a Python toolkit for building evaluations and then generating these summary visualizations, which we call robustness reports, that summarize what a model might or might not be good at. So let me give you a quick, kind of a rough walkthrough of this code snippet, just to give you a sense of how it works and what's actually kind of powering this underneath. So I'll just walk you through step by step. You don't have to read this all the way through. So at the top here, we have loading your data and model in. So you just load a standard kind of here, a data set and some model from Hugging Face who do great work in kind of consolidating all these models together. And we support currently a bunch of tasks in NLP. So things like text token classification, text generation, And we're also, working on kind of adding vision time series, all these things, and I'll talk about that a little bit later as well. Next, we have this idea of running processing workflows on your data. So the idea here is you want to use a bunch of site information or a bunch of metadata in order to do your analysis. This is very common. You can think about, an image data set, for example, and then having labels on it or having metadata on it that allows you to filter, group data, and analyze what's happening on these slices of data. So that's what's going on here, which is we're giving you the ability to run kind of out of the box processing workflows for text processing and generating things like activations and embeddings. And then you can store that alongside your data and use that in your analysis. And some of the actual data abstractions here are pretty interesting, and I'll go over them later. But the idea is you get your data and model, you run these processing workflows to get the site information, and then next, you can create your evaluations by just creating this dev bench object, which is basically a box in which you throw a bunch of evaluations in, and then you can pop reports out of it. That's the rough idea here. So here we have a simple example where we create an evaluation that corresponds to a subpopulation of the data. It tries to look at the tokenized text and then find if the text has certain references to horror movies or something like that. So it's a very simple subpopulation. And of course, you can build your own with the abstractions that we provide, or you can use some of the built-ins that we have, which are common ones for text data. And we support a bunch of evaluations, so things like subpopulations or filtering your data, transforming your data in order to perturb it or attack it. You can kind of generate data by curating kind of data sets and then figuring out manually kind of sampling examples and generating them on your own. Like a common kind of pattern is people like to write down examples, especially with text models, to break a model. So all of those things are possible to do here. And then the abstractions are pretty simple. You just kind of throw in your evaluations, whatever they might be, subpopulations, transformations, and then you add a bunch of metrics. And here the dev bench object is kind of the main driver. It supports all of this kind of exploratory evaluation where you can throw in slices, you can quickly kind of search over them, look at what you have in there, quickly inspect and visualize it using our reports, which summarize all of these different types of evaluations and are kind of an attempt at standardizing reporting that spans a bunch of these evaluation types. You can look at our paper if you want to see how we've actually used it for different tasks. And then you can of course save things and reproduce them, which is very important in machine learning workflows typically, so that somebody else can pick up your dev bench, reproduce your results, and then add to it and continue kind of that process of evaluating and understanding these models. So at a high level, that's pretty much it. Load your data model, create your evaluations, evaluate, and then reproduce and save things after creating your reports. So let me go to the next slide, which is an example of a robustness report that we actually generated using a toolkit. And this is a pretty a simple example for a BERT model on a task that I think is generally only people in research seem to care about. But for the sake of just showing a simple example, this is a reasonable task. It's called a natural language inference. And on the left, what we tried to do was kind of show that we can run a bunch of evaluations that other people think were useful as part of this toolkit. So it kind of is our attempt to show you can broadly span a bunch of evaluations and that the toolkit supports all of these. So on the right, what you see here is all those different evaluation types that I talked about. And those are separated in this report. On the left are the different specific evaluations that we ran to generate this report. At the top are all the different metrics you might want to add, so you can kind of add custom metrics and so on. And here, for example, just to point something out, we noticed that our BERT model is actually pretty sensitive to keyboard character errors. So it's kind of sensitive to these perturbations in keyboard errors. And maybe this is not something that you might want for, let's say, a dialogue chat bot or something like that. So this is kind of the idea here. These evaluations are generally useful and can map onto an interesting task that you might want to evaluate. And currently what we're doing is, on our GitHub, we are making this process even easier. We're unifying it for a bunch of modalities. And I'll talk about that again, as I said, a little bit later. But currently you can just go and pip install and use this. And please give us feedback. Obviously, it's a research project, so we'd love to hear more from folks. So this was the piece about measurement. So I think in summary, I'm trying to kind of bring together all these different ways that you can understand a model in one place, and hopefully learn from that to understand how we can do other things better, like monitoring. So monitoring is essentially this idea, now that we know how to measure things, can we figure out, does performance degrade over time for our model? Right? And what is that performance that the model has? And typically, this happens on unlabeled data. So your model is deployed, it's running on, let's say, production data, and the data is coming in. That data does not have any labels. You don't know, if it's a cat or a dog, but you have to figure out, is my model doing well on that data or not? So that's the problem. And here I'll talk about one work that that came out in ICML this year called Mandoline that we worked on. And this paper basically tries to give you the tools to actually calculate these metrics on unlabeled data. And we have code for this in Robustness Gym, as well as an open source code release. So anybody can just go in and use it. It's like one Python file, literally, I think. So pretty easy to download and use. So what's the setting here? So we have a model. We trained it on a train set. We validated it on a validation set. All of that comes from some source distribution of data, P sub S. So that's the distribution that we think our data should come from. And this is kind of standard machine learning. All this is labeled data. We figure out and train our model, we deploy it. And then once we deploy it, we encounter distribution shift. And that's because our target data, the data that's coming into our production model, is coming from a different distribution, P sub T. And so, bad things happen. What we would like to figure out is, given the fact that the target data that we're getting has no labels, how do we evaluate what's happening there, basically? And Mandoline, which is our work, is a user-guided framework to evaluate models using slices of data. So this connects really nicely to what I was talking about in measurement, where I was describing these ways that you can construct these slices. And then in Mandoline, what we were saying is that now that you have those slices, you can put them to use not just evaluating, but also in this monitoring piece. So it's kind of a dual purpose thing, where we're giving you an extra capability with that slicing that you're doing. So that's the conceptual idea for why this might be interesting to do. And then let's just kind of round it a little bit. So a slice is just a user-defined grouping of data, just to reemphasize. And here, I've kind of shown 3 slices. So negation. So for example, you might take a text sentence and then say, like, find me if this text sentence has the words not or an apostrophe T or something like that. And then if it does, that's a negation sentence. And I'll say it lies in the slice. Similarly for these other slices that are marked. So basically, if you do this process, what you can get is on your labeled validation set, which you have access to, and it's kind of your in-house dev set, you can produce this matrix, which basically corresponds to, is this example in a slice or not? So this example, the first example, is obviously in the strong sentiment slice because it has the word love, and that's how we're defining it. And so in this way, you can kind of produce this almost a summary of your data in terms of these binary numbers, right? So it's giving you this binary matrix representation of your data. And of course, since this is labeled validation set, you can figure out if your model is actually performing correctly on this or not. So you can get like, did my model get this right or wrong, and so on. And then you can get an estimate of your source accuracy or your in-house accuracy, which is, here, let's say for argument, like 91%. Now you can do the same thing for your unlabeled deployment or production data. So the reason you can do this is you don't need any labels to run these slicing functions. You can just run them directly and produce these binary representations. And again, what we provide in Mandoline is an approach that relies on importance weighting, which I won't have time to talk about here in detail, but like the idea is we basically look at, how much we upweight examples that are more likely to appear in the test set or the deployment data, and downweight ones that are not. So for example, if you had 60% of your validation set was, let's say, a male pronoun, so it was kind of heavily male biased, and then on your test set maybe it was 30%, we would want to downweight the amount of emphasis we put on the evaluation on the male slice and upweight the one on the female slice. So that way we can adjust our scores on our validation set where we have labels, and then get numbers on the target unlabeled test set. So here, for example, we might produce an estimate that's 84%, and that tells us, without using any labels, we think that performance dropped by around 7%. So that's the idea here. And in the paper, we describe, different approaches. We use this for text tasks, vision tasks, and so on. And typically, we would see like either performance at par, and in some cases, we would actually get 5 times more accurate than standard baselines that people use for this type of task. And the real power here is being able to use those slices to basically kind of reduce the dimensionality of your data, make it a lot simpler, and then do these importance weighting approaches, which people use here. But conceptually, the main idea is how do we get metrics on unlabeled data, and this provides you a simple approach to do that. So now that we've talked about measurement monitoring, I want to jump into maintenance, which I think is probably the hardest piece of this. And how do we measure and make fixes to undesirable behavior? So the idea here is now that you've measured your model, you figured out, things aren't going quite as well as you'd like, and you've identified undesirable behavior. What are the ways in which you can actually fix that? And here we have a couple of papers, and the second one I won't talk about it, but it looks at these more data-centric approaches. So things like manipulating your data in order to improve performance when you have heavily unbalanced data. But I'll discuss the first one because I think it's hard and interesting. So this is a paper that we have in NACL this year called Goodwill hunting. And the background here is named entity linking. So I'll give a quick background so that you understand what's going on. So named entity linking is a task where you want to map strings or text to things in a knowledge base such as Wikipedia. So for example, if you had a sentence like, when did England last win the Football World Cup? What you would hope that this named entity linker does is that it maps England to the English national football team and Football World Cup to the FIFA World Cup. And then you can use this linker as part of a larger system, let's say a downstream system. For example, that system might be a question answering system. So maybe it's trying to answer this question that you asked. And so here it would want to produce the correct answer, which is 1966. And hopefully, if you have a correct NEL, you'll actually more likely to get the right answer, because of course, if you map Football World Cup to the wrong thing, you're not going to get the right answer. So an NEL is pretty important, and it's widely used in industry across things like Siri or like Google Home and all these different things to understand what's actually being said in text. And in this paper, what we tried to do was analyze and then repurpose off-the-shelf systems. So this is really trying to do this end-to-end thing where we took commercial and academic named entity linking systems off the shelf. So we just kind of took them, didn't tweak them in any way, and then analyzed them using Robustness Gym and produced these nice reports that tell us, different behaviors that you can look at in the paper. And then we picked one particular system that we thought was promising and then tried to guide its behavior for a sports question answering application. And so I'll focus on this repurposing piece here. And what we wanted to do here specifically was we had this kind of error happening in our data, which is you have this sentence, English player, Harry Kane scored a goal in their match against Germany, but Germany was getting mapped to Germany, the country, instead of the German national football team. Because here, obviously from context as a human, you understand that if it says match against Germany, you should map Germany to a football team or sports team of some kind. And of course, Harry Kane is a footballer, so you might be able to figure that out. And so what we tried to do here is actually try to fix this bug in the model in a very targeted way. And why do we want to do this? Because again, if you have a sports QA system, you want to have a model that actually prefers predicting national sports team instead of countries. So that's where you want to guide the behavior a little bit. And what we did was super simple. This is kind of inspired by work in data programming and the Snorkel system, where we relabeled our training set, which was noisy and it was collected from Wikipedia, so it wasn't perfectly labeled in the first place, with a very simple heuristic that was very sports focused. So what we said was, let's try to label, match against sports team as a pattern that generally, so match against is a pattern that's generally preceded or succeeded by a sports team type of entity. So that's just a simple training set heuristic that we used, and then we kind of retrained the model. And in the paper, we have kind of a little bit more analysis, but what we saw was like, just with simple tweaks to the data, where you're kind of taking a more data-centric perspective on how you want to tweak your data, you can get pretty large improvements that guide the model towards the desirable behavior. So here we saw, an absolute accuracy improvement of 25% on these sports errors that they particularly care about in a sports QA application. And that's kind of interesting that you can do this in a systematic way for this pretty complex task or pretty complex system of doing named entity linking. So I'm gonna, start to wind up here a little bit and talk a little bit about, Wishlist and kind of things that I'm pretty excited about as far as malleability goes. And then I'll conclude with some, kind of emerging work that we're doing that I'm pretty excited about. So there's a lot to do in this end-to-end regime of like going from measurement to fixing the problem that you find. And there are a lot of approaches, and some of these approaches we attempted to bucket in that paper, where there's these data-centric approaches that rely on doing data augmentation, collecting more data, doing active sampling, labeling your data, processing your data in different ways. And then there's these more model-centric approaches. And what we've seen is that typically in industry, the experience of people who put models into production is that data-centric approaches tend to be more performant, and they give you more bang for the buck. So that's just in general a pretty interesting kind of separation that we should hopefully study more. And then one thing I'm pretty interested in is understanding how to atomically fix models so that you can incrementally, like software, kind of keep patching models and hopefully produce a model that covers all the errors that you care about, but you don't have to do it in this kind of slapdash way as we do it today, but more kind of atomically as you would do in software. And of course, like what we want to do is understand, at least in the research side, the trade-offs between these methods, and then talk to folks in industry as we are doing today, and figure out where we can actually make progress on these questions. So that's something that is a wish list from my perspective, and especially on data-centric AI, we're doing some work that I'll mention at the end. One thing I'm super excited about is our project called Meerkat, which is trying to build these data panels for doing interactive machine learning. And so the idea here is, I talked about these three different pieces of measurement, monitoring, maintenance, and you need kind of a substrate, a data substrate that allows you to do these things interactively. So I talked about at the beginning this desiderata for malleability, that stakeholders can do these things interactively. And that's where some of the data abstractions that we're trying to build come in. So this is in the Meerkat project. I put a link to a demo at the bottom, but and you can find links to this at the end. But the idea here, in terms of what we're actually trying to do, is, let's say you have a CSV called data.csv that has some data. Typically, you would use pandas to analyze it, but pandas often doesn't work very well for complex data types, and that's where machine learning kind of centric complex data types is where we want to be for this project. So here, what we would do is load in a data panel that has this data, and here what we support is a bunch of different backends in terms of how we actually store and process the data. So for example, let's say the data had image ID, file path, and label. It would get loaded up as this data panel, very much like a pandas data frame, and then you would be able to kind of use it. But what else you can do here is that you can actually define these specialized columns. For example, you can define an image column in Meerkat that basically takes your file path and then recognizes that the column actually contains images, and so you can do image specific operations on it. Similarly, you can also then run machine learning models and produce columns that know that they contain predictions or that they contain embeddings inside them. And so then what you can do is produce, for example, you can run UMAP on a embedding column and produce a plot that shows you kind of the embeddings and other interesting workflows. So this is kind of still early work. We're still a few, I think maybe 3.5 months in, and we kind of have the first version of this built out. So we would love if people would like to use this. And we're building these interesting workflows. So if you have ideas for workflows you would love to see in a data structure like this, please reach out to us. But one of the things that we did do is actually make Meerkat the backend for Robustness Gym. So now it powers all of that evaluation workflows, all those evaluation workflows that I talked about. So that means that because Meerkat supports different data modalities, we've been able to extend kind of Robustness Gym's capabilities to things like image data and other data types. So that's kind of the thing that I'm very excited about, which is taking a more data-centric approach to all of these different things and a more interactive approach as well to let people work with this data, which in machine learning at least is not just your training data, but also your predictions, your embeddings, and your model and its weight. So all of that it needs to kind of fit together in some data structure and make it easier to work with. So with that, I'm just going to kind of close out, and here's some of the papers that I talked about. I'm just going to put them up. And one resource that I'm pretty excited about that I just want to advertise very quickly is this data-centric AI GitHub repository that we've been building at Hazy Research. And it's just a kind of our attempt at trying to build a community around this area of data-centric AI. And if you go there now, you'll see kind of, it has a bunch of pedagogical value in that it has, a bunch of resources and links and discussion of pretty important areas to data-centric AI. And we would love to have people contributing and kind of putting in whatever you think is interesting in that. So please feel free to go there and check it out. And that's it for me. Thanks so much.
Karan, amazing, man. So one thing I want to ask you before we keep moving, I noticed you called one of these projects Mandoline, and right. You may have seen that I'm a bit of a musician myself. Right. Where did the inspiration for that name come from?
I can't take credit for it. It was my advisor's idea. I think if I remember correctly, he said, you're working with slicing. And Mandolines, he had recently bought one to slice, I think it was cucumbers. So he said, maybe you want to name it a mandolin after the slicer I just got. And it kind of fits the theme of the project because he's working with slicing. But it's not that kind of mandolin. It's a different kind of mandolin. Yeah.
Yeah, I now understand that. Sweet, man. Well, thank you for this. We're going to keep rolling. I really appreciate it. And as always, your shirts are on point. Do you only own Hawaiian shirts?
I own like a ton. I own so many Hawaiian shirts. I own probably 30. It's a bad addiction.
That's awesome. Well,
but they're cheap. So I don't I'm still dragged.